Now that we have some intuition for what logistic regression is and what it's doing, let's formalize it. Logistic regression is a classification method. Remember, it's not actually regression. It's classification, and as such, the setup is that we're given pairs of examples, x1, y1, up to xn, yn, and the xi's are going to be d-dimensional real vectors. And the y's, we're going to focus on the binary case. Logistic regression can be extended to multi-class classification, but to keep things simple, we're just going to look at the binary case. So the y's are 0 or 1. And logistic regression is a discriminative model. The model is, we model the y's, we model yi as a Bernoulli random variable with probability sigma of W transpose xi, and these are, each of the yi's are, they're independent. And here, sigma is this logistic function that we talked about, 1 over 1 plus e to the minus a, sigma of a. This is called the logistic function. And the parameter, this w is the parameter. It's a parameter of the model. So this model, being a discriminative model, there's no probability on the x's. The x's are just fixed, non-random. It's not generative. And that's it. That's the model. That's logistic regression. So let's write down actually what the likelihood function is, just to make it, well, I think maybe it's clear. Yeah, actually, let's wait and come back to that when we're going to do the, in a little bit, we're going to try to find the maximum likelihood estimate of W given the data, maximize the likelihood of the data. And we'll see that Newton's method is a good way to do that, because you can't actually solve for W analytically, the maximum likelihood. But first, before we do that, let's talk about some pros and cons of logistic regression. Pros. So some advantages. Maybe one of the biggest advantages is that it's interpretable. Thinking back to this example we talked about here, our motivating example, when we were thinking about being an actuary, and we had this, the variables or the covariates in our data were age, male, female, and cholesterol. And what's nice about this type of model, this logistic regression model, is that these coefficients of the individual variables mean they sort of mean something in some sense. You know, because if W1, say, if W1 is positive, then when the age is getting big, then the probability of death is getting larger. So a positive coefficient means that that variable is increasing with the probability of the event. And if that coefficient is negative, then the probability is decreasing as that variable increases. So it tells you what the coefficients are, tell you something about how the individual variables are affecting the probability. And that's a very nice thing, because you can sort of interpret, after you get the coefficients, then you can interpret what the variables are doing. Another thing that the coefficients tell you is that which variables are more influential in this probability, at least in the model. I mean, not necessarily in real life, it's just a model, but they tell you, they sort of indicate which ones are more influential. And why is that? Because say W1 is very large and positive. Then as the age increases, this is having a very, very large, this is increasing, this is making this dot product increase very quickly. And so as a result, that's going to make the probability change significantly. So a large coefficient means that that variable is highly influential in the outcome. And so if it's large, either positive or negative, it's highly influential. If it's highly if it's a negative value, which is large in magnitude, then it's also influential, because as the age increases, then it's decreasing the probability. Of course, that's highly unlikely, but if you had something else, like amount of exercise or something like that, number of hours exercised per week, then as that got larger, to some, at least to in a small range, then that would be decreasing, probably that would be decreasing the probability of death. Okay, so that's the first nice thing about logistic regression, is that it's highly interpretable. And that's actually one of the main reasons, at least as far as I understand, why it's so popular in fields like medicine and social sciences. Okay, another thing which is very nice, and this is a more statistically nice thing, is that there is a small number of parameters. And as a result, the parameters are easier to estimate in a statistical sense. The number of parameters is d plus 1, because there's one for each of the coordinates of this w vector. And that's a very nice thing, because even as the dimensionality is getting large, the number of parameters is only increasing linearly in the dimension. So that means it's a very simple model in a sort of statistical sense. And that's a very nice property. So as long as it's a good model for what you're trying to model. If it's not capturing certain effects that you need, then that's not necessarily a good thing. But in general, having a small number of parameters is nice, statistically speaking. Another thing which is kind of nice about this is that it's computationally efficient. So that was sort of statistical efficiency, but it's also computationally efficient to estimate the w parameter. And we're going to see in the next video or two how to do this. Computationally efficient to estimate w. And you do it, at least the sort of common approach, as far as I understand, as far as I know, is that you use Newton's method. And it's a very efficient second order method, and it's guaranteed to converge to an MLE. So that's a nice thing also. Nice sort of guarantee there. It's fast. So even though you can't get W in closed form, it's still fast to get an MLE. Another thing, so there's lots of nice things. You can extend it to multi-class, very natural extension to multi-class, even though we're just going to talk about binary. And it also forms the foundation, so I'll just put foundational. This method forms the foundation for some more complex methods like neural networks, and also things called generalized linear models. Okay, so those are some pros. And let's also mention, of course we have to mention some cons. One con is that the performance is not necessarily as good. Performance not necessarily as good as the sort of leading methods, the best performing methods. Of course, it always depends on the problem. This is, I put not necessarily because, if this is actually a correct probabilistic model for your problem, then you would certainly want to use this. But as a general black box sort of method, when people have compared several different classification methods like random forests and boosted trees and support vector machines and all these kinds of things, then they found that those, actually the ones I mentioned there, were actually some of the highest performing ones, that those were as a black box sort of classifier when you throw a bunch of different data sets at it, at least in some a small some studies that I've seen, that logistic regression did not perform as well as a sort of black box. So that's a con. But, but if the shoe fits, wear it. If it's correct, if shoe fits, wear it. If it's an appropriate model for your problem, then it's perfectly fine. Okay, so I guess that's the only con I wanted to sort of mention. And next, we're going to take a look at how to estimate this W parameter using maximum likelihood.